That was pretty intense, and that happens a lot with integration by parts, especially when you have multiple iterations of it within a single problem. Here's one more example that we'll use, and then we'll call this good. And you might stare at this and see the product of two different functions and be like, I see where this is going, integration by parts. And then you might be like, but what made this one really miserable is that instead of an x here, like you did in your previous video, this was an x squared. And the squared made me had to use integration by parts twice because the first time u changes the x squared into a 2x to the first power for my du, but that 2x sticks around inside the integral right here. So I have to use integration by parts a second time to make the x from that 2x down to a 1. So you look over here and you're like, x cubed, you got to be kidding me. You really want me to use integration by parts 3 different times? Like, that's going to be miserable. You're going to run out of room on this page. Turns out you don't. Turns out you don't want u to be equal to x cubed here. How would you know that? My obnoxious answer is probably, well, repetition. Do a whole bunch of these and you'll start to recognize things. But maybe a better answer for the student for how you would know that u cannot be x cubed is if u is x cubed down here, then dv has to be the natural log of x. If dv is the natural log of x, you got to figure out v. Question, what's v? What's the antiderivative of the natural log of x? And you're like, easy, it's 1 over x. No, it's not. The derivative of natural log of x is 1 over x. You're like 1 over the absolute value of x? No, 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 no. You're thinking derivatives, not antiderivatives. You do not know the antiderivative of natural log of x. At least you're not supposed to at this point in the class. In fact, I'll show you in the next video how you can come up with the antiderivative of natural log of x, shockingly using integration by parts. But that's all an issue for future videos. Right now, we don't know the antiderivative of natural log of x. If we don't know the antiderivative of natural log of x, how can we possibly make dv natural log of x? We need to know what v is, and v is that antiderivative. So we're almost forced in this case to let u be equal to the natural log of x and just kind of hope, man, maybe I'll get really lucky and this will work out. If u is the natural log of x, dv is everything that's left over. So in this case, it would be x cubed times dx. With these choices of u and dv, I can now figure out what du and v respectively are equal to. Let's see, du over dx is 1 over x, so therefore du is 1 over x dx. dv is the antiderivative of x cubed, so v equals, and these are going to start to kind of make your head hurt. You have to be really good at these, going in both directions. Derivatives on this side, antiderivatives on this side. It's so easy to write 3x squared right here, but it's not. It's the antiderivative. This is the one where you add 1 to the exponent, but then you have to put the 1/4 down in front as a coefficient. So I get that v is 1/4 x to the 4th power, the antiderivative of x cubed. With all these pieces, I can use my integration by parts formula. It tells me that this integral is equal to, and actually here I got to be a little bit careful. With definite integrals, the way you write them up is a little bit weird. Maybe this is another one of those where I show you what the book does and then I show you what I do. And the short answer for what I do, anytime I'm figuring out a definite integral, when I'm using integration by parts, is I completely ignore the bounds and I solve the indefinite integral first. And then after I figure out the indefinite integral, I just use the evaluation theorem, so kind of tack on the bounds to that antiderivative that I found to figure out my answer. And I'll show you why it gets kind of weird. Using my formula, I first get u times v. So here's my u and my v, and then I want to subtract from that the integral of v du. Here's my v du. A couple of comments. I think I told you that I'm not going to write this step where I show all the parts and then in the next step factor out the coefficients and simplify stuff. When I do these, I typically simplify right in this step to save myself a line. But I didn't want to heap too much on you early on, so I showed these one more time and I'll simplify it in the next step. The other comment is this was a definite integral. So you might think that I should probably put an e and an e cubed here. And yeah, you can absolutely do that if you want to keep track of this notation. However, note that this also needs to be evaluated from e to e cubed. So I guess I would need a line here signifying that this still needs to go from e to e cubed. I think that that gets really messy when you're going through this, especially imagine if you're doing multiple iterations of this. So my personal preference is to leave those off on both these guys and just remember, since it's a definite integral question, at the very end I need to evaluate this guy. But that's just personal preference. At any rate, I'm going to take this 1/4 and pull it out in front of my integral. And then I'm going to note that x to the 4th times 1 over x is the same as x to the 4th over x, which is just x cubed. Ah, how convenient. Right? You start to see that anytime you have x raised up to a power, I'm hesitant to use anytime. Often when you have x raised up to a power and you have a natural log of x floating around, it's really nice to let your u be equal to the natural log of x, because the derivative of natural log of x, namely 1 over x, works out so nicely when you multiply it by powers of x. Right? It simplifies really nice, and you don't end up with a product over here in your integrand, which is good, because if you don't have a product in your integrand, it's a lot easier to figure out the antiderivative. At any rate, we still have a couple steps left. What we want to say is this line is equivalent to, well, when I take the antiderivative of x to the third, I got to change the power to x to the fourth, but then I have to multiply that by 1/4. Note that I wrote 1/4 twice, once for this one and once for the one that occurs when I take the antiderivative of x cubed. And you might be like, couldn't you have just written 1/16? Probably, but I want to show you the steps to make sure that you can follow these. And again, you might be like, shouldn't you put down a plus c here? Aren't you forgetting that? Well, yes, if I'm evaluating an indefinite integral. But remember, all of this work is just so I can figure out this definite integral. So after I figure out this answer, I'm going to evaluate it from e to e cubed. So I guess if you wanted your notation to be really good, what you should do is write something like this indefinite integral is equal to all this work, and maybe this gets a plus c here. And then therefore the definite integral is this same stuff evaluated from e to e cubed. And it's a little bit tedious evaluating things. That's why I often ask you indefinite integral as opposed to definite integral questions, because you can do it, it's just annoying. But I wanted to do at least one definite integral question, just so you see kind of a little bit of the issues in notation in here. This, if you want to be really careful, you could say this equals this equals this equals this, and then start a new train of thought for this and solve it. But if I'm being perfectly honest, I usually leave this out and leave this out, and I just trust that the reader can figure it out, that, oh yeah, this is all indefinite here, but oh, he picked up the definite at the very end, he's good. Maybe that's me being a little bit too loose with my notation, and maybe some other teachers would prefer you're really careful about what actually equals what when you're doing these problems. At any rate, evaluating this guy, first we copy this entire line, except we change all the x's into e cubes, and I put unnecessary parentheses around that just to make it easier for the student to follow. And then we copy this entire line again, except we change all the x's into e's. And now it's up to the student whether you want to call this good, because this is the correct answer, or if you want to simplify this. I just can't help myself. I have to simplify things like this, but I'm not saying that you have to. The way this will simplify is e cubed to the fourth. When you have exponents raised up to exponents, you multiply those together. So this will end up being e to the 12th power. And the natural log of e to the third power is just 3. And that's because the natural log is asking the question, what power do you have to raise e up to make it equal to the thing in the parentheses? And the thing in the parentheses is e cubed. So e to the third power equals e cubed. It's kind of a weird statement to say. Same idea here. Here's e to the 12th. The natural log of e to the first power would just be equal to 1. So applying those two facts yields this line here, which is starting to get a little bit prettier, but I think I can even go further. I have e to the 12th and e to the 12th. Right, 3/4 of these things minus 1/16 of these things. Well, 3/4 is the same as 12/16, and 12/16 minus 1/16 would be 11/16. And similarly over here, 1/4 is 4/16, and 4/16 minus 1/16 would be 3/16. So I have 3/16 of these e to the fourth guys. And now I think this is pretty enough, and I'd probably call this good. You could argue that you could factor out a 1/16 from each of these terms. You could factor out e to the fourth from both these terms. I mean, you could do a lot of different things. Simplify is kind of a subjective term, and it's sort of in the eye of the beholder. I think that this is pretty beautiful right here, so I think I would call this answer good personally, but it's up to you at which stage you stop.